Got it? All right. I will begin. Heavenly Father, we thank you for this day. Thank you for the students. Pray you to help us use this time wisely, that we would glorify you when we do, Lord. In your name I pray. Amen. Okay, so I thought that since not everybody has a chance to take complex, it'd be helpful, perhaps, to just have a quick rundown of like the most important, sort of biggest ideas in complex. And so I'll start with just numbers, right? So what are complex numbers? I'm not going to try to give you an abstract algebra view of it. I'm going to be very geometric. If we take a point, z equals to x plus iy, this is a typical complex number, right? Here we have the real part of z is what we call x. The imaginary part of z is y. These are both real numbers. So formally, set of complex numbers are real numbers multiplied by I and added together. And you multiply them in the natural way. So this is the imaginary axis, as it's called. This is the real. And if we were to look at this and we just make a line to the origin, then the length of this line we denote by what's called modulus of z. So the modulus of z is the square root of x squared plus y squared. All right. But on the other hand, you can look at this as a vector, right? You can look at z as a two-dimensional vector from the origin like that, right? And you can build it from two pieces. You can build it from its real piece, which is this guy down here, right? And its imaginary piece, which is what? Oh, contrast of blue on blue, not so great. So here, its imaginary piece, this one, right? Which we would, as a vector, that's iy. Right? But we could also introduce the standard angle. And the standard angle, which is exactly what it sounds like, the usual polar angle, this guy, theta. Well, you can see what x should be. X should be what? The hypotenuse is modulus of z, right? And then this is the adjacent side, so that's cosine theta, right? Over here, we've got I, absolute value of modulus of z, sine theta, right? Or if you like, the distance, the length of that green thing is just sine theta times the modulus of z, right? So you see what we have is we have that we can build z as the x plus iy, right, which is modulus of z cosine theta plus I modulus of z sine theta. Any complex number can be built in this way. You can try. If you extend theta to other quadrants, it naturally adds the pluses and minuses as needed. That's the whole construction of sine and cosine to more than acute angles, right? To make polar coordinates work. Same here. So z is modulus of z times cosine theta plus I sine theta. And of course you might know we call this of course is the e to the I theta, right? This is e to the I theta. Although, you guys, sometimes in certain books you'll read this as cis theta. Cis theta is e to the I theta. Cis theta is people who are cowards, people who are unwilling to embrace e to the I theta. Oh no, the students will never understand e to the I theta. I need to do cosine and imaginary sine theta. Really? Why would you do that? I'm sorry, cowards. I stand by my cowardly. I stand by my name calling. Let's see here. So we get modulus of z, e to the I theta. There you go. And this, of course, is the what? This is the here, example, if I have 1 over 3 plus 2i, right? I can write that as 3 minus 2i over 3 plus 2i times 3 minus 2i, right? And that's what? Oh, why on earth did I make up this number? Bad, poor planning on my part. 9 plus 4, right? So yeah, great. That's 3/13 minus 2 over 13i, which is in fact equal to yeah, well, this is, if I call this thing I call this thing z, right? Then this is in fact equal to the modulus of z times e to the I theta, but what's theta? See, I did a bad thing. Violating the terms and conditions of this lecture, which is to keep it easy. Like, what's the modulus of z? Yeah, right. Or we could say z is equal to 1/13 times 3 minus 2i, right? And so the modulus of z is 1/13 square root of 9 plus what? 4. Did I do that wrong? I'm sorry. It's fine. Sorry. So that's what? Square root of 13 over 13, which is 1 over the square root of 13. Great. What's my theta? Where is this thing? Good news, it's here somewhere, right? So that means that we're between plus or minus pi over 2, right? So I can find the theta. What would theta be? I can use inverse tangent of, minus 2 over 13 divided by 3 over 13, right? Which is what? Inverse tangent of minus 2/3, whatever that is. Right. Sorry, it's bothering me. This is really not the point of this lecture. Let me get it over with here. 2 divided by 3. Did I have 2 divided by 3? Yeah, 2 by 3. Awful. 0.588. That might be something pretty, I don't know. There's a minus, of course. All right, so anyway, getting to the point. Z is equal to 1 over the square root of 13, e to the minus 0.588, right? Point what? Oh, thank you. Hey, you guys don't need this lecture. All right, good. And of course, that's theta. Now, there's other things you can say here, right? Like, there's a complex conjugation. Z bar is x minus iy, right? For z equals x plus iy, and there's wonderful properties of this conjugation, like z plus w conjugate is z conjugate plus w conjugate. ZW complex conjugate is the product of the conjugates, right? And most probably importantly, we have that the modulus of z squared is equal to z bar, right? So with that in hand, it's easy to prove, this is easy to prove then that the modulus of z times w squared is what? It's zw times zw conjugate, which is what? Reorganizing things, z bar, w bar, which is what? Modulus of z squared, modulus of w squared. But being that the modulus is non-negative, we can take the square root of that and get the multiplicativity of the absolute value, or the modulus. So modulus of zw is modulus of z times modulus of w, right? This is very special to complex numbers. In other algebras, you can't do this. Anyway, there's another way we could have looked at the last example, right? We could also looked at that as z is equal to like 1 over w, right? Where w is 3 plus 2i, you know? And so I could tell you without further calculation that w in that previous example would be root 13 e to the 0.588i, right? More generally, if you have z is equal to modulus of z times e to the I theta, then what's 1 over z? 1 over z is 1 over modulus of z e to the I theta, right? Which is what? It's 1 over modulus of z e to the minus I theta. So the polar form of a complex number is very useful for thinking about transformations of complex coordinates. Like, what is this geometrically? You know, suppose I start with this being z, and this is length 2. What's 1 over z look like? So what's the modulus of 1 over z? It's 1 over the modulus of z, right? So the reciprocal of this would have length 1/2, right? And it would have the same angle that way, right? In other words, it would be at minus theta. So when you take the reciprocal of a complex variable, you're doing what? You're flipping, looks like we're flipping over the x-axis, and if our length is longer than 1, if our modulus is longer than 1, we're going in, right? What would happen though what if I was like over here? Geometrically, what would go on? Hypothetical. Suppose I'm over here. I've got z is equal to, I don't know, 2 e to the what? What would this angle be? Something like 3 pi over 4, perhaps? Right? Right. Where's e to the minus? That's just down here, isn't it? Yeah. So that's 1/2 e to the minus 3 pi I over 4. And, of course, 1/2, right? If you're on this, you just flip from positive y-axis to the... So it's always a flip over the x-axis, right? And it's either... If the length is longer, if the modulus is longer than 1, it's making it shorter. What happens if the length is smaller than 1? Like, what if I started with 1/2? I reciprocate, I get to 2, right? So you start thinking about this, chase this idea down. If you think about what reciprocation does to the unit circle, it's kind of interesting, right? If I start with z in here, where's 1 over z? If this is the unit circle. And then 1 over z is like down here somewhere, right? I can't do the angle right, but it's something like that. So it takes every point inside the unit circle and does what? Flips it outside. It takes every point. If I was to start with z, if I start with w here, where minus w, rather 1 over w would be like somewhere in here, right? These are not quite to scale, but you get the idea. And then what does reciprocation do to the unit circle? It fixes the, well, yeah, it just flips the unit circle, right? Anyway, I was going to try to give a best of talk. It seems like I have diverged from that a little bit. But these are ideas that we can use to analyze questions about complex graphs, right? If you look at the form of the polar form of a complex number, you can answer a wide variety of geometric questions with just this kind of machinery, right? Now, I've spent entirely too long on that. What does it mean for a function, then, to be complex differentiable? What do we mean? Talk about complex differentiable function. What's that mean? If we have a function going from complexes to complexes, right, is differentiable. I should say complex differentiable at z equals to z naught. What do we require? This following limit exists. F prime of z naught will be the limit as z goes to z naught of what? F of z minus f of z naught divided by z minus z naught. Does that look familiar? It should. This is the difference quotient from calculus 1. It's just now that the limit is taken in complex numbers, but it's the same epsilon and deltas and everything else. So if I tell you things like f of z equals to z squared, what's f prime of z? You can tell me. It is in fact 2z. Very good. See, you too can do complex variables. How about this? F of z equals to e to the z. What's f prime of z? It is in fact e to the z, right? But what does that mean? This. Let's look at that for a second. So we're saying the limit, and we'll look at z. Let's look at. Let's consider this one. Let's look at f prime of 0. Okay. For f of z equals to e to the z. If you look at this limit, this becomes the limit as what? Limit as z goes to 0 of what? E to the z minus 1 over z. What does that actually mean? What is e to the z? Right? How would you define e to the z? It depends on how your complex variables course goes. One way you could define it, if you don't do integration first, is you could just give it in terms of real functions. So e to the z, this is how I would probably do it. Put it right here. So let's, curses. E to the z would be e to the x plus iy, which is e to the x times e to the iy. All right? So you could define it to be the function which is e to the x cosine y plus I e to the x sine y. So this could be the definition for the complex exponential, right? That would be a decent transitory definition. I mean, transitional rather. And what is this then? This is the limit as x comma y goes to 0, 0, right? And that is apparently e to the x cosine y plus I e to the x sine y, and then we're subtracting 1. We're dividing by x plus iy, right? So if you'll allow me, I'll simplify that a little bit. This is the same as dividing by x squared plus y squared and multiplying this whole thing by the conjugate, right? That, by the way, I buried the lead. What's the real purpose for the conjugate? It's that 1 over z is z bar over z bar, and that gives you a formula for the inverse of any complex number. That shows you, without a doubt, that for a non-zero complex number, it has a multiplicative inverse. But anyway, using it over here to make real the denominator, you're faced with that. So when does such a limit exist? What does it mean for that limit to exist? It means that the real and imaginary part of that limit separately exists. Well, those must not be too bad, right? What are those limits? They can't be too bad, right? It's the exponential. It's your friendly neighborhood exponential. It's harmless, right? So you got e to the x times x cosine y, and then what else? Plus e to the x y sine y divided by x squared plus y squared. That looks to be the real part. Plus I times e to the x sine y times x. Then what? Minus y e to the x cosine y divided by x squared plus y squared, right? So great, you can take those limits. It seems very possible. Oh yeah, I forgot my, and also over there, I forgot about that one. So I'm supposed to have minus x out front here. And I'm supposed to have a plus y out back here. Thank you. Now you guys know what it's supposed to work out to, right? What's the derivative of the exponential at 0? It's e to the z at 0. These limits are supposedly working out to 1, right? So this apparently limits to 0, and this apparently limits to 1. You remember in Calculus 3 when we showed you how to do these kinds of limits? They were painful, right? And these are worse than the ones we show you how to do. Because we show you how to do polynomial ones. These are unpleasant. So what do we do? I mean, how is it that we know the derivative? How is it that we know that the derivative of the exponential is the exponential? Do we actually work out this limit ever? We do not, all right? We actually do not. We define the log, and then the exponential is the inverse of the log function, and then the chain rule gives you the derivative of the exponential is the exponential again, is one way you could do it. Or better yet, you define the exponential by its power series, then you know its derivative is itself. The other way you could do it, of course, yet another way, is the Cauchy-Riemann equations, right? So what's the Cauchy-Riemann equations about? Here's the short version of it. If f is equal to u plus iv, this is complex differentiable when u and v are continuously differentiable. In other words, you can calculate partial derivatives of them, and the partial derivatives are also nice. They're continuous functions, all right? And ux is equal to vy, and vx is equal to minus uy. So these are partial derivatives, okay? So, for example, for e to the z, we had e to the x cosine y plus I e to the x sine y. So for this function, you can see that the u is this, and that the v is that. So ux is e to the x cosine y, right? And that's also equal to the partial derivative of v with respect to y, right? So there's one of the Cauchy-Riemann equations. How about the other? Vx is e to the x sine y, and that is minus the partial derivative of u with respect to y. So I've got a function. It has continuously differentiable real and imaginary parts. Satisfies the Cauchy-Riemann equations everywhere. Therefore, the complex exponential is complex differentiable, even though if I try to calculate directly from the definition, even at 0, the nicest of all possible points, it's horrible. The theorem still gives me that complex exponential is differentiable, and there's a little bit more. Here's the rest of the theorem. And f prime of z, you know what it is? It is ux plus ivx. In other words, it is partial f partial x in the natural way. That is what the complex derivative is. So what is ux plus vx for this example? Well, that's e to the x cosine y plus I e to the x sine y. Yay. That's e to the z. So there you go. Now, to actually prove that the Cauchy-Riemann equations do this, it requires advanced calculus. Advanced calculus is what tells you that if the function is continuously differentiable, then it's differentiable. And then differentiability paired together with a particular piece of algebra requires the Cauchy-Riemann equations. Anyway, enough about that. So this is just the quick and dirty. If you want to know if a function's complex differentiable, the question is, does it satisfy the Cauchy-Riemann equations, and is it nice? All right, if it's not nice, if it's got division by 0, that's still a no-go, right? And so if you're in complex right now, maybe Dr. Sprano's given you problems which the Cauchy-Riemann equations work a lot of places but not some others, you know. Another terminology that's important, a function is said to be holomorphic. What's that mean? So like, here's my function domain. Bad choice of letters. Let's see here. There we go, that's better. So suppose that this is a point P. Then F is said to be, and S is a subset of the complexes. All right? S is holomorphic at P if there exists some open neighborhood around P on which the function's complex differentiable at each point in there. So like if I can find some little, like this, and if F is complex differentiable at each point in there, then the F is said to be holomorphic. So.
Is there a go-to function that you have that is used to show what to make it a complex differentiable?
When is what?
Is there like a go-to function that's used in examples typically to show like something that's not complex differentiable?
Oh yes. My go-to example would be f of z equals 2z bar. This is not complex differentiable because you've got x minus iy, so you got u equals to x, you've got v equals to minus y. So here we get ux equals to 1, uy equals to 0, vx equals to 0, vy is minus 1. Right, 1 is not equal to minus 1. But it's interesting, you can define partial f partial z bar to mean a particular combination. I don't remember it right offhand, unfortunately, but this being 0 is equivalent to the Cauchy-Riemann equations. So another way you can look at the Cauchy-Riemann equations is saying it's a function which is just a function of z, but not a function of z bar. And sort of generically, if your complex function has a formula, has a z bar in the formula for it, it's not going to be complex differentiable. For example, I can tell you just from looking at this that this is not complex differentiable. And I can also tell you that partial f partial z bar is actually equal to z. So there's one point, and only one point, where that's complex differentiable.
So is the converse true? Is that
the origin.
If there's any function that is not comprised of z bars, does that mean it's guaranteed to be differentiable?
With the proper context, I think so. I mean, z and z bar give you a complete set of variables for complex numbers.
Yeah.
So if it's not a function of z bar, not a function of z bar means that partial f partial z bar equals to 0. Partial f partial z bar equal to 0, when you actually write it out, is the same as the Cauchy-Riemann equations. So, all right, enough about this. What does it mean for a function to be complex differentiable, though? What does it mean for f equals to u plus iv with f prime of z not equals to 0? What's that mean? There's a laundry list of things that, I mean, what this means is that the function is what's called, it's a conformal. It gives you a conformal transformation. Conformal transformation. In other words, if you map z to w equals to f of z, all right, if you look at that transformation, if you've got a curve like this and a curve like that, so gamma 1 and gamma 2, in the z, over here in the z plane, and you feed those under f and look at their corresponding curves, say f composed of gamma 1, and over here f composed of gamma 2, all right, then something beautiful happens. There's a chain rule, d dt, of f of gamma of t. You know what it is? It is equal to df dt, dz rather, f df dz of gamma of t times d gamma dt. So this, whatever it is, if f prime of z is non-zero, then this is just a non-zero complex number, which means it's something like m e to the I gamma, well, e to the I theta. Whatever it is, it's a fixed complex number. And whatever points, whatever two paths you have that go through that point, if you look at the derivative of the path over here, the velocity vector is related to the velocity vector of the path over there by multiplication by a fixed complex number, which means that the velocity vectors, like here, if this is v1, then this one would be v1. It would be rescaled. It's longer, and it's also rotated by theta. And if this is v2, the velocity vector on the second path, then this is mv2 rotated by theta, like that. So they both get rotated the same angle, and they get dilated. So what's the thing that's preserved from here to here? It's the angle between the paths. So like this angle here, if I called that beta, the angle here would also be beta. And so that's why it's called a conformal. A conformal transformation is one which preserves the angle between intersecting paths as you map the path from the start to the end. Now, the length doesn't have to be preserved, all right, but just that. So that's one meaning for a complex function. We can look at it as a conformal transformation, which is very interesting. The other thing that's really, really interesting is that if you look at ux equals to vy, if you differentiate that by x, you get uxx equals to vxy, right? But that's equal to vyx, which is what? Let's say partial y of vx, right? But what's vx? Minus uy, right? And that is minus uyy. So what did we get? We get that uxx plus uyy equals to 0. And you can do the same for v. This makes u what's called a harmonic function. So the component functions to a complex differentiable function are harmonic. That does not assume that the derivative is non-zero. I need non-zero to get this to make sense. Otherwise, I would just have everything mapping to a constant. So we have, a complex differentiable function is one that satisfies the difference quotient. It's one that satisfies the Cauchy-Riemann equations. It's a conformal transformation if it's non-zero. It has component functions which are harmonic, like that, right? And the u and v are said to be harmonic conjugates. And I feel like there's another character. I mean, you could also say it's just a function of z. It's a holomorphic function. Sometimes that gets lumped into. These are all characterizations of complex differentiable functions. Integration. Poor planning on my part. So if we integrate over a curve, f of z dz, the way this works, it's almost too simple. It's the integral over c of u plus iv dx plus I dy. It actually means the integral of u dx plus, u dx minus v dy over c plus I times the integral of v dx plus u dy. So you can look at it as a pair. You can actually look at it as a pair of real line integrals, a complex linear combination of real line integrals of corresponding functions. It somehow is calculating something about this. This would be like the line integral of over c of what? Of u comma minus v, right? In the usual Calc 3 notation. This would be the integral of like v comma u dot dr in terms of line integral notation. It's both of these at once, right? That's what the complex integral is. What is it? I don't know. I don't have a good answer for that. But I can tell you how to calculate it. The way to calculate it is very simple. We use a parametric approach. So you just integrate, say, t1 to t2 of f of gamma of t times d gamma dt dt. But that's a complex multiplication. So here we're looking at a curve that's going from gamma of t1 to gamma of t2 like that. A good example to start with would probably be the integral along, let's say, the circle centered at z naught, radius r, of, let's say, z minus z naught to the power n dz. So this is my curve. So I want to just do one circle. So the picture is here. Here's my z naught, right? And we'll let it be, counterclockwise, okay? So I need to come up with what's a parameterization for the circle. So like maybe this would be e to the it times r, right? So z naught plus r e to the it. And if I let t range from 0 to 2 pi, that should get me full circle, right? What's dz? The dirty secret is you can ignore this and just calculate formally and it works out. Like, what should dz be? Well, z naught's a constant. It differentiates to 0. And this gives me r I e to the it dt. That actually makes sense when you work out all the formalism. And so I've got integral from 0 to 2 pi. What's z minus z naught? Z minus z naught is, it's r e to the it, right, to the n. My dz was r I e to the it dt. What do I get? I'm assuming r is a real constant here, so we can pull that out. We're going to have r to the n plus 1, right? And I've got an I. I'll pull that out. Ooh, it sounds painful. Integral from 0 to 2 pi. Issue. E to the, looks like e to the nit plus it. Nit plus it. There's got to be a better way to write that, though. Oh, yeah. N plus 1 times it. There we go. It's probably a more civilized. I'll tell you, I. There we go. Now I feel better about it. I times n plus 1 times t. There we go. That's what we got. And then, oh, yeah, don't forget about your dt. But one of the things I failed to tell you because I was too busy talking about minutia that doesn't matter to anyone, is that the complex exponential is 2 pi periodic, right? In other words, if you have e to the z equal to e to the w, that's true if and only if z is equal to w plus 2 pi I k for some k in the integers. The argument has to differ by a 2 pi multiple of the imaginary number, because that gets fed into the sine and cosine, and they're 2 pi periodic. So if you just go back and look at the definition I wrote for complex exponential, those are equal only when the z and w differ just by an imaginary piece, which has to be 2 pi multiple. Anyway, so just saying. So how does this work out? That's I r to the n plus 1 over I times n plus 1, right? E to the I times n plus 1 t, evaluated from 0 to 2 pi, which is, well, these are, I mean, actually that's 1 minus 1, okay? Because the sine piece is 0 and the cosine piece is 1. This is 0. What is the one case where my calculation breaks down? At the origin, yeah, in some sense that's fair. But setting aside the case that that r is equal to big R is equal to 0, would be, I think, what you're really getting at. What about when n is equal to minus 1? See, when n is equal to minus 1, I can't divide by n plus 1, right? And when n is equal to minus 1, it's simpler than what I did, right? What happens when n equals minus 1? Yeah, so I guess we could rewrite it this. It's z over z minus z naught, right, is equal to the integral, well, excuse me, yeah, what did you say?
No, never mind on that.
So everything here would be legit. It's just that is e to the 0, right? So we've got in I, right? And that's r to the 0 as well. So we got I times the integral from 0 to 2 pi of what? Of, well, dt. Which is what? That is 2 pi I, right? Now, the reason that this function works out to 0 is very simple. The antiderivative of this, if you look at f of z equal to 1 over n plus 1, z minus z naught to the n plus 1, this is an antiderivative. For z minus z naught to the n, right? Unless what? N equals minus 1. That's right. And so if I integrate around a loop, I can use the fundamental theorem of calculus. That's also available for complex variables. Like if I have the integral of df dz dz, I can do f of p minus f of q, just like that, if I'm looking at a curve that starts at p and ends at q, like that. There is a FTC for complex analysis, just the same. So something special about this n equals minus 1 case. And
It kind of looks like, it almost looks like you're integrating
with what?
Yeah. I mean, because it is like one of those.
Well, so I don't, sadly, I have planned poorly today. So I can really just tell you the formula and maybe work an example if I'm really lucky. But there is a joyous thing that happens here. We get the following result. Well, let me just get straight to the punchline. this is really I guess, the penultimate theorem of complex analysis, Cauchy's residue theorem. It states the following: if you're integrating a function along a curve, then that's equal to 2 pi I times the sum of the residues at zj. J equals 1 to however many you got, and that's for a simple positively oriented contour. So let me give you an example. If I was integrating, say, 1 over z plus 2 minus 1 over z plus 4i, let's say, all right, and I'm integrating over c in the counterclockwise direction, and suppose c is the circle of radius 3, centered at the origin. So the residue, what it is you calculate what's called a Laurent series. All right. The Laurent series for the complex integrand, it captures singular points for the function. And these integrals are only going to be non-zero when there's some sort of singular point inside the contour. That's what happened over here. See this? When n is not equal to minus 1, this function's harmless. Well, that's not entirely true. N is minus 2, it seems like it's got a singularity, right? But the quirks of complex analysis are such that if this is minus 2 or minus 3 or minus 4 or minus 10, it still integrates to 0 around the unit circle. There's something special about that minus 1 power. That's the residue. The residue is actually the coefficient of the minus 1 power in the Laurent expansion. These are Laurent expansions already. This is the Laurent expansion at minus 2. This is the Laurent expansion at minus 4i of a given function. Okay, so if you look at this integrand, there is at minus 2 a problem, and at minus 4i there is a problem. This is not our problem because it's outside the circle. And so the residue theorem applied to this function would just give me, tell you what, I'll add some numbers here to make it fun. 13 and 17, there we go. Feel better? Now you can see what's going on. So this one, so the residue of this function, well, let's say the residue of 13 over z plus 2 at, usually we put a, like minus 2 here or something to say where it is. This is just 13 times 2 pi. Well, excuse me, this is just 13. But I'm supposed to do what? I'm supposed to multiply that by, I can't remember there, 2 pi I. So it would be 26 pi I would be the answer. And the other piece doesn't matter. If I take another curve, and the curve looks like this. Ooh, no, none of that. Ooh, whoa, 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 whoa. Don't want any self-intersections, but. Like that. And suppose it's counterclockwise, right? In other words, positively oriented, like that. It doesn't matter what it is. If it encircles these two guys, then I pick up both residues. So if this is my C2, the integral over C2 of the same thing would be 26 pi I minus 17 times 2 pi I. So at the end of your complex analysis course, what you learned is that you can calculate integrals of complex functions around curves by simply finding where the functions misbehave and expanding them in Laurent series about that point. Now the question, of course, is how do you actually find Laurent series for complex functions, right? These are stupid. This is like I give you x squared plus 3x plus 2, and I say find the Taylor series centered at 0. Well, it's already centered at 0, and it's already a Taylor series. This is dumb. You know, it becomes more fun when you actually have to do some work to find the Laurent series, but this is the sort of the lowest level of example I can give you. Sorry, I should have devoted more like a half hour for this stuff. I must go, unfortunately. See you guys next week. We have a next week? What's next week? What's next week supposed to be about? You're like, you're the teacher, you figure it out. Tell you what, I'll go look at our schedule and see if there's anything I'm supposed to do.
You're supposed to like take
What's that?
pictures of us.
Oh, paper! Hooray!